Okay, right. Okay, so good afternoon, everyone. So thanks, first of all, to the organizers for giving me the opportunity to present some recent work that I did on machine learning and resampling, as you see, for parameterizing unresolved processes in multiscale dynamical systems, especially atmosphere ocean models. And this is work that I did with my colleague Wouter Eeling and PhD students Nick Verhul here at CWI. So here's a very brief introduction to the challenge of parameterization. For numerical modeling of atmosphere and ocean, it is well known that there are all kinds of small scale processes that cannot be resolved explicitly in global computational models because the range of skills is just too broad. So you see a little depiction here of on the left there's a computational grid covering the entire Earth, and you see a lot of model grid boxes. Right, that's what you use to discretize the partial differential equation for atmospheric flow, say the primitive equations. But of course, within each model grid box, and you see that on the right, there's still a lot going on that cannot be resolved by this global computational model. And here you see cloud processes and convection that are giving an important effect that should be taken into account in the computational modeling of the atmosphere, but it cannot be resolved explicitly. So how to represent the effect of those processes in a simplified way, that is essentially the challenge of parameterization. Now, this is a challenge that's been known for a long time, and I want to focus here on two relatively recent sort of ways of approaching this problem. One is to use stochastic methods for parameterization, right? So to include some type of randomness in the way the effect from the unresolved skills is represented. And you see here, I mean, this is something that's been pursued now for a little over 20 years, I guess. Tim Palmer has been especially a vocal proponent of this. One of the first people to push for this approach, and you see here a snippet of a paper from 5-ish years ago by Judith Berner, and a lot of other people, sort of giving an overview of what had been done by that time. So that's one, say, approach. The other one is data-driven parameterization. So rather than using the physical intuition and physical insight to build a parameterization, you can also rely on data. Data, for instance, from highly resolved numerical models that are then simulated on a limited time and space domain. Now, this is something that I've also worked on myself. So initially, this was mostly about sort of, say, fitting stochastic processes, right? And you see a couple of references there. And of course, over the last, say, 4 years or so, the use of machine learning, especially deep learning, has become very popular, and there's for this purpose. And there's a lot of papers that are pursuing this, and I cite here a couple of the earlier ones. Rashb et al. Focusing on atmospheric processes, and Bolton and Zana more on processes for ocean modeling. Now, what I want to talk about in this in the rest of this talk is essentially an approach that I've worked on to bring these two say lines of approach, so stochastic and data-driven machine learning, together. Right, a lot of the deep learning work that has been pursued to develop parameterizations has been deterministic. So once the neural nets for deep learning has been trained, it's effectively a deterministic mapping from the resolved skill state to the unresolved skill state. And of course, in a stochastic parameterization, this is something you don't want to be deterministic, but random. So that's what I will be talking about essentially. So, and I'll be talking about this in this sort of simplified setup. You see here a coupled dynamical system of macroscopic degrees of freedom, denoted X, and microscopic degrees of freedom, denoted Y. And there's a coupling through this sigma quantity You see it's a two-way coupling. X and Y are both coupled to each other. So this is an ODE setting, and I'm going to go one step further in simplifying the representation by going to a discrete time setting, as you see here. And moreover, the coupling that you see here at the top. So I'm going to focus on an additive coupling, as you see here. I mean, there's nothing about the method I'm going to say more about. In principle, that could not deal with multiplicative feedback, but I'm going to focus here on additive, and those are also the computational examples that I've worked on. There are also cases of additive feedback. Okay, so the aim here, of course, is to be able to simulate X without having to resolve Y. So Y are the small scale degrees of freedom, microscopic degrees of freedom, and resolving all of those is very expensive. The dimension of Y is typically much, much higher than of X. So what we want to be able to do is to simulate X for a long time without having to resolve Y. And we want to get, at least that's my aim in the methods that I will be discussing here. I want to capture the long-term statistics of X correctly. So the probability distribution of X and the temporal correlations. Right? So that's the aim. This is not about finite time forecasting. It's really about getting the long-term statistics correctly. And of course, to do that, we somehow need to parameterize the feedback that has now become this quantity R that you see here. I hope you can see my mouse pointer. We need to parameterize this feedback R in terms of X, in terms of the macroscopic degrees of freedom that I want to simulate. Okay. Now, the essence of the approach that I've been pursuing is on this slide. And the idea is to evolve this R quantity by random sampling from a conditional probability distribution. And that distribution is shown here. Again, I hope you can see my mouse pointer. It is the distribution for R at the next time step, given the current and past states of R and X. Okay, so I have both from the macroscopic state X and from this feedback R. I have the current and the previous states, and given all those states, there will be a probability distribution for the next time update of R, and I want to sample from that distribution at each time step. Right, so and that then, of course, is done in tandem with updating X according to the model that I already have. Right, so this capital F essentially embodies the physical knowledge that comes essentially from the partial differential equation, which is then discretized into an ordinary differential equation. Right, so it combines both physical modeling, that's the F, and the data-driven part, which is for the parameterization, that's the R here. So I hope you can see that this is effectively a stochastic parameterization, right? Because there's random sampling from this conditional probability distribution. Right? So I'm not taking the expectation, I'm sampling from the distribution. And moreover, it has memory because there's the current and past states of R and X that you see here that are essentially forming the condition for this distribution. And to parameterize in a way that is both stochastic and has memory, there are theoretical motivations for doing that to come from Moritz-Zwanzig theory, which I will not be discussing here in the interest of time. But there's good theoretical motivation to do it that way. Okay. Now, of course, the distribution I want to sample from is unknown in general. It's typically extremely difficult. Practically infeasible to derive this distribution, to derive an analytic expression for this distribution. But of course, I'm not interested in the distribution per se. What I want to be able is to sample from it. Right? So I want to be able to draw samples from it. And that gives us an alternative to trying to derive this distribution. And it is to use data to draw samples from. So here we're going to assume that we have data. We have observations of both X and R, denoted here with the superscript O. And again, the data source can be high resolution simulations. Sometimes it can even be physical measurements, for instance, from satellite or radar data. In any case, we assume we have those observations, and then we can use resampling of the observations to approximate sampling from the conditional probability distribution that I want to sample from. Okay, and then effectively, this is the reduced model that I have with the resampling parameterization. I'm denoting now both X and R with the tilde over it to make clear that it is the quantities from the reduced model, right? So without the tilde, it's from the highly resolved model. With the tildes, it is the reduced model. So at every time step, what needs to be done? We update X tilde again with the capital F and adding the so the resampled value of R tilde, and to update R tilde, we're going to sample randomly from this set here, the set of observations of R, where we have a feature vector in the reduced model that is close to a feature vector from the observations. And those feature vectors are shown here. So it's the current and past states of R and X. That's anyway how I represent them here. And of course, it's possible to simplify that to say, well, I don't need the X, only the R, or vice versa, or you can skip certain time steps. That is all possible in this setup. I've denoted it here in the most general way. Right? So there's a feature vector, both that you defined on say the space of the observations and on the space of the reduced model variables. Right? And I want to find the feature vector in the observations that is close to the current feature vector that I build up from the quantities in my reduced model. And this way of resampling is very much reminiscent of what is known as the local Markovian bootstrap that was developed or proposed by Paparodidis and Politis, as you see here at the bottom, and it has also all kinds of similarities with KNN resampling. K nearest neighbor resampling was proposed by Lal and Sharma in the context of hydrological modeling. Okay, so here's a little example how that resampling goes. So here you see a long time series of R from the observations, and in red you see the most recent time history of R in the reduced model. So what I do is I search for segments, time stretches in the observational time series that resemble the red one, right? So the reduced model one as much as possible. So let's say these are the 5 that are most resembling this this time series here, and then right, so here you see them all lined up, synchronized in time. And of course, what I do is draw one of these 5 blue-red dots as the next time updates for my reduced model. Right. So, for instance, here it could be the bottom one. So there's a non-zero probability for all 5 of them. Right. And then that is my next time update for R. Let me go back one. Okay. So I was just about to discuss how we can do resampling by binning, and binning is essentially just discretizing the feature space, right? So the space that we need to sample from. That we need to find to compare the feature vectors in by discretizing it in a number of non-overlapping bins, and all in quotes that we need to do is find the right bin. So the idea here is that we look in the observations, we look at all the feature vectors, and with each of them is associated a next. Right, so I'm for each of these bins in the feature space, I'm looking at all the observation vectors there, and then I collect the next time updates in the observation, so R at time step j plus 1, in a set of data. And that's the set of data I'm resampling from. Right? So that's the idea of binning. Let me go to a figure to make that a little clearer. So let's say here that we have a one-dimensional feature space that's on the horizontal. In the small gray dots are observations. So what I do is the value on the horizontal here, it's a position value in a simple model that you see here that you can find in the paper mentioned here. All that needs to be done here is find in which of these vertical slabs, so the value of the current value of Q is lying, and then given that I can sample. Let's say it's in this one. So let's say Qi is 0 or a little below 0, and then all that needs to be done to update is sample one of these gray dots that sit in this slab here. Okay, so that's the idea of binning, and that worked well for us on a test model. It's the Kac-Schwanzig heat bath model with a 3-dimensional feature space. It gave good results there. So I refer you to the paper mentioned here. But the one drawback of doing binning is that when your feature vector has a dimensionality much larger than 1, you run into curse of dimension. Right? So this binning gives you a curse of dimension problem. So what can be done there? Well, instead of binning the space of the feature vectors, we can also bin the space of the next time updates. Okay, so that's what's done here. So the space of the next time, so the space in which these R quantities lie, of course, is much lower dimension than the space of the feature vectors, because these R values are only at one time point, and there's not the history that is part of this space. So we bin the space of the R updates, and then to find to sample from the right set of values given the feature vectors, we train a neural net. Right, so there's a neural net we train that essentially what is supposed to approximate, given the feature vector in the observations, what is the probability distribution over all these bins of the next R time update. Okay, so given the feature vector, I want to train a neural net to predict a discrete probability distribution for R over the next time update. And that is for machine learning, that's a relatively straightforward problem. It's a problem of probabilistic classification, and we can tackle that with what is called a quantized softmax network. I'm not going, in the interest of time, into how that goes exactly. Just summarize here what then this reduced model with this QSN type network does. So given the feature vector from the reduced model, I need to update R, right? So the R at the next time step. That goes through 3 steps. I evaluate the neural net. So given the feature vector, I evaluate the neural net that gives me a vector of that is a discrete probability distribution. Then I randomly sample one of the bin values according to this distribution, and then given that bin, right? So this bin BM, I randomly sample one of the R observations from that bin. Right, and I want to emphasize, as you see here below, this is really different from giving a direct neural net prediction of the next time update of R given the feature vector. Right, that would be a really different way of doing this. Okay, as I said, I'm going to skip over the quantized softmax network. Also, how to do with an R dimension that's larger than 1. I refer you to the paper for that. Let me just show you some numerical results from a test model. It's what is known as the 2-layer Lorenz 96 model. It's a much used test model for developing new parameterization methods. And it consists of two sets of coupled ordinary differential equations. It's a nonlinear set. And here, indeed, the X are denoting, say, macroscopic degrees of freedom, and the Y's are denoting microscopic degrees of freedom. And there is the coupling through this R quantity that you see here. Okay, now we consider two parameter settings with this model. Right? So there's one that's much used that gives you a unimodel PDF for the model variables, but there's also a more challenging one. It's non-standard. Oh, sorry, let me go back one. That gives a bimodal probability distribution for the model variables. Right? And here you see some numerical values for the settings of the model. I especially point to the value of epsilon 1.5, which means that there isn't really much time scale separation between the X and the Y degrees of freedom here. Let me go over this one. So here, this is the unimodal setting. What you see here on the left, especially, is the probability distribution for any X degree of freedom in this Lorentz model. In the black pluses are what you get in the full model, and the blue line is what you get if you use this QSN resampling parameterization. So it's a very close fit here. And on the right is the probability distribution of R. But of course, the most important here is the probability distribution of X. And then the feature vector that we used for this consists of these two quantities. So it's X at the current time step and X 9 time steps, numerical time steps ago. Right? So this is a relatively small feature vector. Now, the bimodal setting, as you see here, so the parameters are a little different here. And this is a much more challenging one. So what you see here, again, on the left, the black pluses are for the full model data, and in blue, it's with the this resampling parameterization. What you see here, that's with the feature vector, it's even already contains more information than we had before. Of course, so the result here isn't good at all, right? So the model with the resampling with this feature vector doesn't capture this bimodal behavior of the full model at all. Now, what we did then is extend the feature vector with many quantities. So what you see here at the bottom is now we have a feature vector with a much longer memory. And the only reason we were able to do that is because we used this QSN resampling instead of the simpler binning approach. Right? So with the QSN resampling, we can have a very long feature vector. And here it consists of the current and past 74 states of the X vector. So it's a really long memory that we include here, but grace to that, we were able to capture this bimodal behavior of the X variable, right? So the distribution of X of the full model quite well. And the same goes for the R vector. Okay, so let me go to my conclusion slides, because time is also pretty much up. So as a short summary, so what I present to you a way to use machine learning for stochastic parameterization of small scales, right? So it's by resampling using a quantized softmax network for probabilistic classification. There are other ways to use a machine learning for stochastic parameterization. There isn't much work on this yet, but I should mention at least one paper by Gagne et al. From a few years ago who used GANs, generative adversarial nets, to do this. Secondly, there was the memory dependence that I discussed, especially in this last example. It comes in through the feature vector, right? So you can make it quite long. So you can have a long memory dependence in this parameterization. And finally, there's a degree of physical consistency to using resampling as a way of parameterization, because the only R quantities that we use are the ones that we draw from the observations. So those are the R quantities that are really observed in a high resolution model or even physical measurements, right? So that gives a sort of physical consistency to this resampling approach. Okay, let me leave it at that. Thanks for your attention. I'm sorry about the technical hiccups that we had, but I'm glad I was able to finish this talk. So thanks again. Here's the two references and some funding acknowledgements for the work that I just presented.